Right. In this example, we're going to be looking at a specific kind of differential equation. You may notice this is something called the Bernoulli equations or Bernoulli equations of this form. It's dy dx plus p of x y equals q of x times y to the n. This should look very, very familiar to you. It should look very similar to the form of integrating factor problems that we have solved earlier. The difference is here, of course, if you're paying attention to the right-hand side here, the y to the n, it makes this problem a lot more difficult. And depending on what kind of values p and q have in terms of their functional relationships, it can be even more challenging. So the question is then, how do we go about solving something of this nature? And a clever substitution we can make is that the substitution, we substitute that v equals y to the 1 minus n, allows us then to rearrange this equation into a form that allows us to actually solve. So let's take a look at an example here. So let's imagine we have the equation dy dx is equal to um, something of the form maybe like 3 over 2 x y equals 2x y. Okay. Uh, you may recognize that this could also be given in the form something maybe like 2x y prime equals 4x squared plus 3y squared. So just recognize that the formation of the thing where the y prime, of course, is the dy prime, dy d prime, dy dx. So just be careful that the form may not always be presented in a way that looks immediately like it could be written as a Bernoulli function. But this way allows you to use a little bit of algebraic manipulation as massaging them into a form that may be a little bit more helpful. Let me go ahead and hide that with a napkin. Nothing classier than that for a video. Anyways, all right. So if we're trying to solve this differential equation, then we want to recognize a couple of things. So we're going to identify the components, if you will, of the Bernoulli equation. So recognize that phi of x in this situation then is going to be to negative 3 over 2x. Q of x is obviously the negative 2x. No, sorry, I said negative, I meant positive 2x there. And n is equal to negative 1, since the y is in the denominator here. And that means that 1 minus n is going to be equal to a positive 2. Okay, so that means then that according to our substitution, then that v is going to equal y squared. And another way of saying that is y is then equal to v to the 1 half, solving for y and taking the positive root. Okay. All right. Now we do need to substitute in for dy dx in terms of v. And one observation to note is that dy dx is equal to dy dv times dv dx in the change of the variables there. Okay. So we know dv dx and we know dy dx from our relationship here. So dy dv, if I take the derivative here with respect to v, is going to give me a 1 half of v to the negative 1 half, and then dv dx is actually what we want to know. And so our substitution then for dy dx is going to be this combination here. All right, so let's go ahead and plug everything in to this differential equation, writing in the substitutions that we've already stated. So we should get 1 half v to the negative 1 half dv dx. Okay, so that's the dy dx part, and that's going to be minus 3 over, that's a 3, over 2x. And then we have v to the 1 half, and then that's going to equal 2x v to the negative 1 half. Okay. Let's see. It looks like v to the minus 1 half, v to the 1 half. So it looks like if we do something like multiply through by a v to the 1/2. That's actually going to be a really nice, helpful thing. In fact, if we make it a 2, in fact, if we multiply by this quantity, yeah, so imagine like we're dividing by this quantity basically. So we're going to get dx by itself. I think a lot of things are actually nice things are going to happen. So dividing everything through by dv 1/2 dv dt is the same thing as multiplying by 2v to the 1/2. And so that's going to give me dv dx. So you can think of it as either way. I'm either dividing by this or I'm multiplying everything by 2v to the 1/2. Those cancel. The 2 is going to cancel here, and then v to the 1/2 plus v to the 1/2. That's going to give me a minus 3 over x v. The 1/2 plus 1/2 gives me v. And then let's see, 2 times 2 is going to give me 4. I'm going to have an x, and then v to the minus 1/2, and adding it to a v to the 1/2, that's actually going to reduce to just a 4x. That did simplify the problem very nicely. And that's when you know you have a good substitution, is after the substitution and maybe a little bit of arithmetic or algebraic manipulation, it formulates into a problem that is much simpler to solve. And now this should look very much like an integrating factor problem. So here, put p in parentheses here for the integrating factor would be the negative 3 over x. And if we integrate that, you're going to get a natural log. The natural log is going to cancel out. And so you're going to get, and that the integrating factor, like the example we saw in class here, is going to become an x cubed to the negative 3 because of the negative there. Okay. Don't forget the sign. I just forgot that. This happens when you do this in your head. Okay, so you have a negative 3 here from the negative 3 here. So that's going to give you an x to the negative 3. That's going to be the result. If you're kind of wondering what I mean, this is negative 3 over x dx. I want to integrate that. The negative 3 comes out. This is e to the negative 3, the integral of 1 over x dx. This is the natural log. That's really tiny, sorry. So this is e to the negative 3 natural log x. This comes up as an exponent. And then this becomes e to the natural log of x to the negative 3. These are inverses, so they reduce to 1, and you're just left then with the x to the negative 3, as I was stating. I was actually just verifying that it was negative x to the negative 3 there. So it does turn out to be the case, which means that this side reduces simply to the derivative of the integrating factor, so x to the negative 3 times v, that I want to take the derivative of. This is the product rule of that result. And then over here, I'm multiplying 4x times x to the negative 3, which is, of course, 4x to the negative 2. Okay. So integrating both sides, this is the antiderivative already, so that cancels out pretty quickly. This is going to be x to the negative 3 times v is equal to, this is the negative 2, adding 1 and dividing by it, you're going to get a negative 4 over x plus a constant. This is a 1 over, so I'm going to multiply everything through by x cubed. And if I do that, then of course these will reduce, and you get v is equal to x cubed divided by 1 is going to give me minus 4x squared plus a constant times x to the third. And now solving back for v was here, we made the substitution that y was v times x. Going back up here, we made the substitution that I'm looking at the wrong part. V is equal to y squared. So this is y squared is equal to cx minus 4x squared. And so if I wanted to, I could take the derivative, not the derivative, sorry, I could take the square root of both sides, but that would depend on the constant value of the initial conditions. So it is explicit up to a power of y as a function of x, and that is our solution for this differential equation. All right, I hope that was helpful, and I'll see you in the next